Yeah, they have this GoToMeeting set up so that every time you log in, your mic is muted, because sometimes they have like 1,000 people in a meeting, and if everybody came in without being muted, everybody starts talking at once and they have no way to proceed. So they mute everybody's mic when you come in. So you have to kind of remember to do that. Luckily, you can still hear me when your mic is muted, so I can always tell you that. But okay, so lines, rays, and planes. That's what your text message said?
Yes.
Okay. Well, we dealt last week with a lot of lines, right?
And angles, but we're not working on that yet.
Right. An angle is made up of two rays.
Yes.
That's one ray, that's the other ray. Whatever
And what
angle
would the end
results...
What would the end, okay, what would the end point be?
Well, it kind of goes forever. When I put arrows on it like that, it doesn't really stop.
It means they go on forever.
Yes. A ray
If there are no arrows, then it's a line segment.
Yes.
It stops at the endpoints.
Yeah, exactly. In other words, if I put a circle and I put a line in that circle, that line stops there and stops there.
And those 2 points, like, could be
forever.
A and B. So it would be, imagine those points are A and B, line segment A and B.
Right. So that's what you would call that, is line segment AB. Now, I still honestly think that unless, do you have a book yet, Bolton?
Textbook? Yes.
They did give you a textbook?
Yes.
Let me turn my camera on for a second and see if it's the same one.
You want me to get it?
No, you can probably just tell me. Hold on a minute. Just a second. This one?
Can't see anything yet.
Oh, sorry. Can you see it now?
Nope.
You can't see my face on the webcam?
Nope.
Okay, why don't you get your book and tell me who the authors are.
Okay. Okay, but this might take me a bit, okay?
Sure.
Okay, got it.
Okay, is it, does the top of it say McDougall-Lytell geometry?
Yes. Yes.
And the authors are Larson, Boswell, and Stiff at the bottom?
Who?
Larson, Boswell, and Stiff.
It says Canold or Canold, too.
Okay. Yeah, that's just an additional author.
Yeah.
Okay, so we have the same book. That's good. Now, which means very shortly you're going to be getting into proofs. If you don't have any specific problems, first of all, our tutoring sessions should always start there. If you have problems to cover, particularly if you don't know how to do them, you want to bring those to the table, and then we'll go over them.
Okay, I don't have homework today. I don't have homework.
No problem. I think our best bet is to go back and continue on the path that we were on before you started school, which is to cover lines and angles, triangles, circles, rectangles, things like that. Because you'll get to that, and it'll definitely be helpful to you. Planes are a little tough to deal with. I'm surprised they started you off with planes. You know what lines are, you know what rays are. A plane is like that. Only planes can be at right angles to one another. They can be at any angles. If I had one plane, the reason planes are going to be a little tough for me is because I'm not that good of an artist. It's hard for me to draw planes. But you can see that if I put...
Do they have to be a parallelogram?
I'm sorry, what?
Do they have to be a parallelogram?
Do they have to be what?
Do planes have to be parallel?
Parallel. No, they don't.
Do planes have to be?
No, they don't
No,
have...
parallelograms.
Well, hold on. I understand your question. Do they have to be parallelograms? No, they don't. In other words, anything, if you put your hand out in front of you, make it flat, that's a plane.
Yes.
That's a plane. Now put your other hand, make it flat, and make those two planes be perpendicular to one another.
Okay.
That's what planes are. In other words, I can make that plane 30 degrees, I can make it 49 degrees, I can make it 90 degrees. So planes can be, in other words, this is a plane even if it's not a parallelogram. And this is a plane, even though it is a parallelogram. But I would rather postpone our discussion about planes. You're going to have things like skew lines and questions like that, but when you're dealing with planes. But I think you would be best served at the moment by continuing on with triangles. I think that's these. Yeah. We didn't do any of these, did we? We kind of looked at one, I remember.
Yeah.
We were out of time when we got...
We did these.
We only,
no, we did these.
We only did this.
All of these.
No, I think we only did this.
Yes.
Okay. And how did we do this one? How did we figure out x?
We did all of these on this page. All three angles must add up to 180.
Okay.
So if there's 40 and 60, then x must be 80.
Okay, good. How about number 2? What's the value of x?
Okay, so if that's 20 and 40, which equals 60, the b angle, whatever b is, that must, I'm going to call it b, it must be 120. So 120 plus 60 equals 180. So x must be 60.
Correct. And notice something about that. That's called an exterior angle, x. And it's always equal to the sum of the two angles that it's not next to. In other words, x is a linear pair with what you call b. What's another way to define that angle other than b?
I don't know.
A, B, D.
Oh,
Hold on a minute. In other words, when I have an angle, let me redraw this triangle. First of all, you see why that's called an exterior angle?
Yes.
And you can have exterior angles
Okay,
in any of the three angles. If I extend that line,
so the interior angle.
that's also an
So the exterior angle. Okay.
So here, let me label.
X is an exterior angle.
I'm going to label that 1, 2, and 3. What's x equal to?
3. X is equal to 60.
Well, in my diagram, there's no numbers on it.
Ah.
So x is equal to 1 plus 2.
Yes.
What's y equal to?
Y must be equal to
same exterior angle formula.
Ah.
So y
it must be to 3 plus 1.
Exactly. So whenever you have a triangle and you have an exterior angle, that exterior angle is always equal to the sum of the two angles that it's not a linear pair with. In other words, y is a linear pair with 2, so therefore y has to equal 1 plus 3. X is a linear pair with 3, therefore x has to equal 1 plus 2.
Okay, I'm getting it now. Yep.
Good. Let's have a look at problem number 3.
Okay. In the figure above, x equals, okay, 180, that would have to be, 110, that'd have to be 70, right?
Correct.
70 meaning 70 plus 60 is 130, so that would have to be 50. So x would have to be 130 degrees.
You had it halfway through. When you said x has to be 60 plus 70, that was the answer.
Okay.
Okay. In other words, there's the hard way to do this and there's the easy way.
Sorry.
No problem. Here's the hard way. I know that's 60.
The thing is,
this
we haven't
is 70. Now I know that has to be 80, which means this has to be...
Wait, what?
Excuse me, my mistake. Good catch. This has to be 50, right? In other words, if I solve this triangle, and then since that's 50, that has to be 130. But that's the hard way to do it. The easy way to do it was to immediately, the moment I figure out that this angle here is 70, well now I know that x is an exterior angle, so it has to be the sum of that plus that. So I can get there quicker if I use the exterior angle theorem.
Mm-hmm.
Now, when I talk about theorems, geometry is full of theorems. It's a theorem that says an exterior angle is equal to the sum of the two other angles that it's not linear with. That's a theorem, okay? Another theorem is the Pythagorean Theorem. Let's talk about the Pythagorean Theorem quickly. Pythagorean Theorem only applies to right triangles, excuse me. And a right triangle has to have a 90-degree angle in it. Okay? Now, what the Pythagorean Theorem says is that x, the hypotenuse, squared, has to equal 3 squared plus 4 squared.
Yes.
That means
So,
x squared equals 25, so x equals 5. So anytime I give you 2 out of the 3 sides of a right triangle, you can always solve for the third side, no matter
yes.
where it is. Now, this triangle here...
What if it were like the 3 that was missing?
Okay.
Like, I had a problem on this.
Let's get this right now, because you'll always want to use this technique.
Okay, no, like, can I ask a question? We had map testing today, and there was a question. It was a right triangle just like this, except we had measurements where the 5 and 4 would be.
Okay.
So.
Okay, so here's how I do
it. It was like 40 for the hypotenuse, 20, and then...
Okay, give me an equation. Give me an equation I can write for the picture I've drawn.
So, no, but what I'm trying to say is it asked me to do that and then find the angle of a certain...
Okay.
Of 2 rays.
Yeah, that's fine. That's a different problem altogether. In other words, there's 2 very special kind of right triangles. And we might as well get into that now. Let's go over right triangles. First of all, let's look at the one you're looking at here.
Mm-hmm.
What equation can I write? What's the Pythagorean Theorem say?
So a squared plus b squared equals c squared. So what you could do is you could square 5.
In this context.
And,
so what's the equation? Give me the equation that applies to this triangle.
Okay.
Start with short sides. X squared
plus 4 squared equals 5 squared.
Okay.
But what really would apply to this certain triangle, these set of numbers, is 5 squared minus 4 squared equals x squared.
Notice that's what I'm going to do. My next step here is to subtract the 4 squared, so I get this. Now, what I would like you to do is always jump to this step right there. In other words, if you're solving for a side that is not the hypotenuse, it's always this. The short side is equal to the square root of the hypotenuse squared minus the other short side squared. Okay, so you'd come up with 3. Let me give you a bunch of these, because the sooner you get how to do these efficiently, the better off you're going to be. So, what we said was that the short side, no matter which side you're solving for, the answer always begins square root of.
Okay, so x equals 7 squared minus 6 squared. So the square root of both those.
So 49 minus 36, that's what x is, the square root of 13.
Okay.
Okay, and that's what I would write there, is square root
And 13 does not have a very
that's the answer. You don't want to change that to a decimal. You want to leave it as a radical.
Okay.
Okay. Another one.
Okay, so x, is that a 2?
A 2 and a 6 now.
Okay. So x equals the square root of 6 squared minus 2 squared.
Okay, good.
So 36 minus 4 equals 32. X equals the square root of 32.
Can you simplify that?
4 squared? No.
4 root 2. And
oh, yes.
let's make sure you know how to simplify that. I'm pretty sure you're pretty good at these. It's the square root of 16 times the square root of 2, right? 16 times 2 is 32.
Yes.
And then that reduces to a whole number, so I can pull it out like that. Okay? I need an easier eraser on these things. I have to punch too many buttons to erase. What's x equal to here?
Okay. So x equals plus 3 squared.
Square root of. Always start your answer square root of.
So I thought okay, never mind. So 2 squared is 4 plus. So 4 plus 9 equals 13. So x equals the square root of 13.
Right. In other words, there's only 2 kinds of problems, right? There's one where you're solving for the hypotenuse, and then that's always a plus sign. And there's another where you're solving for one of the short sides, and it doesn't matter which short side you're solving for.
Okay, but what if you want more than that? What if, let's call the lowest interior angle, the bottom right interior angle. What if you're trying to find the degree of that?
Okay.
Because I got a problem today.
That's trigonometry. And
yeah, I got a problem today asking me how to do that.
Okay. Let's talk about that. There are 2 very special kinds of right triangles. I'm not going to talk about all of them, but the very 2 that you run into a lot are what's called a 30, 60, 90, and another one is called the 45, 45, 90. And these are the only 2 you really have to concern yourself with for a while. Okay? What's important to know about these 2 triangles is what their relative dimensions are. Well, I call them my unit special triangles. Why unit? Because the opposite side of the 30 is always 1. Or the opposite side of the smallest angle is always 1. Well, if that's 1, that's square root of 3, and that's 2. And over here, that's 1. That has to be 1 also, because it's an isosceles triangle. And this is square root of 2. So, if you can memorize these 2 pictures with their dimensions, then you can solve a lot of problems. For example, let's say I have a 30, 60, but it's bigger than this 30, 60. It's got a hypotenuse of 4. Now, the 2 triangles, I'm going to erase this other one just so it doesn't get in our way. These 2 triangles are called similar.
Yes.
In other words, they have the same
diluted,
3 angles. They're both 30, 60, 90 triangles. So
they're diluted, right? Dilution, is that what it's called?
What's that?
Dilution, is that what it's called?
No.
Dilation? Yeah,
that's a little different, but yeah, you're close. Dilation is similar concept, where you take an object and you leave it the same exact shape, you just make it bigger. The thing is that if I tell you you have a 30-60 triangle that has a hypotenuse of 4, you can immediately figure out what this short side is and what this short side is. And the way you do it is you figure out what's called the similarity ratio. You get the similarity ratio by dividing the hypotenuse by the other hypotenuse. So what's the similarity ratio? How much bigger is the bottom triangle each side than the top triangle?
It's doubled. It has to be doubled.
So what does that make this side over here, opposite the 30?
Okay, that would have to be the square root of 6.
No, 2. In other words, it's got to be double the other short side.
Yes, I know that one. I just didn't know which one you were referring to.
Oh, I see. I was pointing, but it looks like you probably can't see my cursor.
Yeah.
So what's the bottom side?
Maybe just make a dot there, and that's the square root of 6.
Actually, it's 2 root 3.
Oh.
In other words, you multiply the outside of it by 2, not the inside. These two triangles are similar, and not only do they have the same 3 angles, but each side is proportional in a 2-to-1 ratio. So, if you know these two special triangles, the 30-60-90 and the 45-45-90, then you can figure out the dimensions from just knowing one dimension. Let me give you another example. First step, what's the similarity ratio?
It's 3 times 3.
What's the hypotenuse?
The hypotenuse would have to be 6.
And what's the bottom side?
3 times 3, the square root of 3.
3 times the square root of 3, exactly. Okay? So if they're asking you about triangles and asking you to give an angle, it can only be one of these two. It's either going to be a 30-60-90 or it's going to be a 45-45. Now, in other words, they are never, ever going to give you a problem, well, not ever, they will once you get to trig, where they say, what's theta?
Oh, they did. That's exactly what it was.
Have they given you any trig?
Maybe I just got that high.
No, it would be very unusual if they're giving you this problem on the right here. Because theta is equal to the inverse tangent of 2 over 3. And you probably don't know what that means. Huh?
It had that 0 with like the cross through it.
Well, that's what geometry uses for angles, is Greek letters. And that's theta, but it could just as easily be delta, or alpha, or beta. In other words, angles usually use Greek letters.
Yes.
Whoops. Let's just do it this way. In other words, if I give you, there's also another very common right triangle that is called a 3-4-5 right triangle. Notice that this squared plus this squared equals that squared, right? 9 plus 16 equals 25. So it indeed fits the Pythagorean theorem, but now if they said, what is that angle right there? Let's call ABC. So what is, you could call that angle C. You could call, in other words, all of these mean the same thing. Theta equals angle C equals angle ACB equals angle BCA. Notice how each of those mean the same angle. Just for some terminology. Okay, if you want to define an angle by all three letters, then you need to use this. In other words, if I make an extension there like that, now I can't really call that angle C anymore. I'd have to call it angle ACB or angle BCA. You understand why?
Mm-hmm.
I could still call it angle theta, but I can't call it angle C, because is angle C this theta or is angle C that delta right there? You don't know.
Mm-hmm.
So the only time you can use a single letter is when it's at the vertex and there's nothing else there.
There's nothing else supplementing it?
Yeah.
It's not supplementary?
Well, or, I mean, I could draw all kinds of pictures where you wouldn't be able to, let me draw another triangle here. I cannot call this angle A, because is that angle A or is this angle A? They're different. In other words, is angle 1A or is angle 2A? You don't know. So if I want to define angle 1, I need another letter. Let's put a point over here called D. If I want to define angle 1, I have to call it angle DAB. If I want to define angle 2, I can call it angle BAC, not D. I could define angle 1 as BAD, but if I'm defining angle 2, then I'm going BAC.
Yes.
I'm going to write it like that. And the vertex is that middle letter, always.
Mm-hmm.
Okay, good. Just wanted to talk about terminology. All right, let me think here what the best next thing to do is. Let me give you some right triangles. I really think that this book here that I was using makes a mistake by not starting with right triangles. Right triangles is where it's at in geometry. Okay, so I'm going to give you another right triangle. That's 45, 45, 90. This side is 3. Now, because this is one of those two special kind of triangles, you only need one side. You don't need 2 out of the 3 sides. You only need one side to fill out the rest of the triangle. Here's my unit one, and this is why you need to memorize it. Unit 1 goes 1, 1, root 2. So what's the similarity ratio here?
Okay, so 3, 3, and 3 times root 2.
Good. Now, let's make it a little harder. Let's make this side 3. Now what's the similarity ratio? Always do big to little. Always do big to little. Always do the big is in the numerator, the little is in the denominator.
Okay.
In other words, as opposed to little to big. Little to big works fine also, but
I
it's,
don't. How
well,
would you do?
similarity ratio is 3 divided by root 2, correct?
Yes.
Okay. Rationalize that. In other words, there's a problem with that, right?
Mm-hmm.
You cannot have an irrational denominator. So you have to rationalize it.
I don't know what the square root of 2 is, though.
Well, you don't need to. In other words, when you rationalize, first of all, forget converting these to decimals. They may have you do that for a while, but you're never going to want to do that in real math. Okay? The way I rationalize this is I multiply it by the number 1, which in this case is root 2 over root 2. I can multiply any fraction by the number 1 without changing its value, right?
Mm-hmm.
And now that gives me that. So that is the same as that, only the bottom answer is better because it has a rational denominator. It's okay to have an irrational numerator. You just cannot have irrational denominators. So this is my similarity ratio. What's side y?
Would it be 3 times the square root of 2 over 2?
Yes. In other words, you take the similarity ratio and you multiply it by that, 1. So you get 3 root 2 over 2. And in the 45, the sides opposite the 45s have to be the same, always, because this is also called an isosceles triangle, meaning it has 2 equal sides. And when you have 2 equal sides, the opposite angles are always the same. In other words, if I draw an isosceles triangle like that, that means those 2 sides are the same. That's what those hash marks mean.
Mm-hmm.
Well, when you have 2 sides that are same, the angle opposite also has to be the same.
Mm-hmm.
So if this was...
and then you can tell that third angle.
Right. So if that's 50, that's 50. And then, like you said, if both of those are 50, then I can figure out that one there.
So all you need is one angle.
Well, that's true. If you knew it was isosceles. In other words, if I told you that it was 80, you'd be able to tell me these two are 50. If I told you just one of them was 50, then you'd know this one's 50 and you can figure out the 80. So yeah, with isosceles triangles, they're particularly simple to figure out because you only...
As long as they have the hash.
What's that?
As long as they have the hash marks, which they should.
Right.
Which they should.
Right. And as long as we're talking different kind of triangles, those look similar, but the only way I really know that they're similar is if I did this. You familiar with the double and the triple? In other words, what that means is this angle is the same as that angle. This angle with the 2 lines is the same as that angle. And this angle with the 3 lines is the same as that angle.
They're just different side lengths.
What's that?
The side lengths are just different.
Well, yes, they are, because we can see that this is a smaller version of this. So I would not be able to say that that is the same as that. They're not.
Mm-hmm.
If you gave me 2 triangles, though, that were oriented a little different, in other words, instead of that triangle being like that, let's say I draw it like this. Now it's kind of hard to see. There's a word in geometry called congruent. Two triangles are congruent if they have the same three sides and the same three angles. In other words, if I label that like that, put 3 hash marks through that, well, those have the same three sides, right?
So they must have the same three angles.
And you're right, they necessarily have to have the same three angles. But having the same three sides is actually more important because that makes them congruent. Two triangles are congruent if they have the same three sides and the same three angles. You could have two triangles have the same three angles that are not congruent.
But not the three same sides. Not the same three sides.
Right. In other words, if I draw a triangle like this and I make it like this, well, those two triangles are similar, but they're not congruent.
Yeah, congruent means the sides are the same and the angles are the same.
Yes, exactly. And there's some rules that you use to test for congruency. And that's one of the first things you'll do when you get into triangles is test for congruency. You do congruency before you even do similarity. But that is congruent with that, and that is similar to that, but not congruent. So there's two kinds of things. There's congruency and there's similarity. And you'll spend a month on congruency, on proving that two triangles are congruent. You don't just have one rule. It's not just all three sides and all three angles. Sometimes I can prove congruency by just side, angle, side. In other words,
yeah, you only need two sides and one angle.
there's a couple of things. If I have side, angle, side, those two triangles are congruent. In other words, you usually need three things. Side, side, side makes for congruency. Side, angle, side makes for congruency. Angle, side, angle makes for congruency. In other words, if I redraw this picture, and I don't say that those sides are equal, but let's make these two angles equal. Now, do you see
angle equal does not mean
that definition? In other words, I have angle, side, angle when I read it in a row.
Yes, but angle does not make for congruency. Correct. It makes for similarity.
Exactly, because I could just have a big one of these, same three angles, and it's similar, but it's not. It
can be. It can mean congruency.
Yeah, if the sides.
It can mean congruency, but it doesn't.
But what I'm trying to get at is that to prove congruency, you don't need all three sides and all three angles. You need as little as side, 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 that's congruent, or side, angle, side is congruent, or angle, side, angle. Now, it's important that you understand these terminology here. You see why this picture is angle, side, angle.
Mm-hmm.
And do you see why that picture is side, angle, side? In other words, you start with one and you go in that direction and I get side, angle, side. And if I give you another triangle that has same side, same included angle, same side, you don't have to label it. I know they're congruent. Okay? So these are the three tests for congruency. But we're kind of getting ahead of ourselves here. Let's go back and look more at these triangles here. Even though they're not right triangles, it's still a lot to learn about triangles from this picture. Hold on. Okay, so how are we going to figure out x in this picture? Geometry is frequently multiple steps. In other words, it's rare that you get a problem you're going to be able to solve in one step.
So are you talking about question 44?
Yeah.
No, 4?
Question 4.
Okay. So, first you would have to take the 30 and the 55 and add them up to get 85. Then you realize that 115 would have to equal that other angle. So 115,
okay, define
so 180 minus 100.
that you're talking about here. Which angle are you solving for?
Okay, I'm solving for angle DBC. Okay.
That's already solved for. That's already 55, DBC.
Oh, no, sorry, BDC.
Okay.
Or CB.
What is BDC equal to?
115.
I think it's 95.
Oh, yep, I get that now.
Okay. Now what?
95, meaning the other side would have to be 85. So that would mean BDA would have to be 85. So 85 plus 50 equals 135.
So what's x?
X would equal 55.
45.
Oh my god.
It's okay.
Sorry.
Remember, one of the best skills you can have in geometry is subtracting from 180. Let's talk about that for a second. I'm subtracting that 135 from 180, right? This digit always adds to 7, not 8. You see where these two are always going to add to 7.
Mm-hmm.
Unless they both end in zeros. In other words, if this was 130 instead of 135, now these two numbers are going to always add to 5. But usually you're not dealing with zeros, and these two numbers always add to 7. So when you're subtracting a number like 95, has to be an 8. Those have to add to 17, not 18. You see that?
Mm-hmm.
And that's my first step, is to put that first digit. Now this digit's easy. I know this digit's the complement of 5 with 10. So that's always an easy digit to get. But the digit that most people get wrong is that one right there. And the reason they get it wrong is because they try to make these two add to 18. And they don't. They add to 17. Or 7 in some cases. All right. Now, there's a different way to do this problem that's actually a little quicker. The way you did it wasn't bad. You figured this angle, and then you figured this angle, and then you figured that angle, right? 3 steps, correct?
Mm-hmm.
Well, what's that angle right there?
So
Look at
CAB. CBA.
CBA. What is angle CBA? Look only at the
100.
outside triangle.
That would have to be 100.
Correct. And if that's 100, what's x?
45.
2 steps, right? So
Yes.
it was actually easier to go this route rather than to figure out this angle BDC and then BDA and then x. So there's usually multiple ways to go about solving any triangle. And you're always better off the shorter way. But it'll take you a few tries. The trick to this problem is recognizing that we actually have 3 triangles here, right?
Mm-hmm.
We have this triangle, excuse me, we have triangle 1, we have triangle 2, and we have triangle 3, the big one. And sometimes you want to look at the big one to start. And that's what we did, and that's how we got the answer in 2 steps only. Okay, hold on. Same page, huh? Hold on. All right. Just a second. Ah, I saw what I was looking for. Took me a while to see it. Those arrows right there. That's the one I want. Hold on. Okay. You know what bisect means?
Bisect?
Problem number 5. I don't know if you can see it or not. We'll end on this one.
Okay, zoom in on that. Okay. Okay.
It says if
In the figure above,
BD bisects angle ABC. Bisect means what?
like double intersect?
Splits into 2. 2 equal parts.
Okay.
That's what it means. If I bisect a line, like that. If I bisect an angle, it's like that. Okay, in other words, angle 1 is equal to angle 2, side 1 is...
It's basically a triangle being divided into 2 triangles at one of its vertexes.
Yeah. So they want to know what angle BDC is. So which one can we solve first?
So we already know angle BDC is 90.
No, it looks 90, but we don't know that.
Okay.
You can't, if there's no...
Oh, no, I got it now.
If there's no 90 degree thing, you cannot assume it's 90, even if it looks like it.
Okay, yes. So if 50 and 30 add up, that would mean angle ABC would have to be 100.
Okay, which means angle AB, which means angle DBC is what?
50.
There you go.
That's very weird.
And BDC is what?
That would have to be 100.
Yeah. In other words, this is a very typical geometry problem. You have to solve for one thing first, and then a second thing. You can never do these problems in one step. You generally have to solve for whatever you can solve for. In this case, we were able to solve for that angle there. And once we solved for that angle, now I was able to solve for what they were looking for. But that's the way most geometry problems unfold, is you have to solve for multiple things sometimes before you can get to your ultimate thing you're trying to solve for. Bolton, I have a 6 o'clock I got to go to, so I'm going to let you run.
Okay.
I will talk to you next week.
Okay.
Okay. Have a good week. Bye-bye.